All right, let's see here. Okay, so can everyone see this okay, or do we need to kill some lights? You can. But do you want to open that a little? I don't want you to be, you're okay? Is everyone okay like this? All right. Okay, so here's the problem that you were asked to do. It was the helicopter problem. And here was the function. We actually did that in class last time. We created the function. And then here's the work for it. So I'm just going to talk through it. I'm not going to work it out. Once you were told to graph a quadratic function, then it's just those steps. So the first thing is to determine that it opens down. That's true because the a in the problem is negative 16, so it opens down. The next thing was to determine the vertex. Vertex was negative b over 2a. You should have gotten from that 0.023. And then to get k, you take that 0.023 and you plug it into the function, which is all this right here. And that would give you 200.09. Okay? Then you go and you draw a quick sketch. You plot your vertex. It opens down. You should have two X intercepts. You set this thing equal to 0. I forgot to put equal 0 here. So you set this equal to 0. Then I use a quadratic formula. And also notice that in the quadratic formula, I use t instead of x because our function has the variable t, not x. You may have put x. That's just because of habit. You know, you always want to solve for x. But in this problem, t is the variable. So our final answer should be t equals whatever. And our two answers here for x-intercepts were negative 3.51 and 3.56. Then you determine the y-intercept. By plugging 0 into the function, you get 200. So that's all the information that you were supposed to have gotten on that quiz. And then after that, you were supposed to graph it. So your graph may look very different. It all depends on the way you scaled everything. But you should have your x-intercepts, 3.55, negative 3.51 or something like that. And then your y-intercept and your vertex should have been pretty close to each other, right? Because your vertex was 0.023, which means just barely to the right. And then 200.09 is just barely above 200. So it's kind of tough to graph this, but I'll be looking to see that you got all the information correct. Okay, so this is the picture, right? Now what we're going to do is go back and answer the questions from last time. Because the questions didn't say graph it, right? It said, how high does the bomb go? In other words, what is the highest point? And then how long until kaboom, right? Those were the two questions. So we should be able to go back to our graph, and we need to kind of talk about what things are here. The x-axis is actually our time axis, right? Because t is our variable, t is time. And our y-axis is actually our d, our distance, our height. Because it's d, right? D is the distance. Now, what was time measured in this problem? Time was measured in seconds, though, right? And what was our distance measured in? Feet, right? Go with me? Okay, so what I'm going to do is below this, I'm going to do a new page. I want to draw kind of a different graph so you can kind of see what's happening a little better. And I'm going to exaggerate this, okay? Let's say that this is 200 feet. That's what's happening at our y-intercept, right? So that's exactly at the moment, right before, right, at 0, at time is 0, before the bomb is released. The helicopter is the bomb is 200 feet high, right? But then we let it go, and we said from last class it would go up just a little bit and then start coming back down, right? So what happens is I start the clock, the bomb goes up a little bit, right? And then it hits a maximum point and starts to come down. And then it eventually hits the ground down here, right? So if the original problem was how high did it go, wouldn't that correspond to whatever that height is right there? Which is which part of the information that we gathered? It's K, right? Remember, this point is the vertex HK. K is our y coordinate. Our y coordinate is how high that point is off the ground. So what is it for us? 200.09 feet. That would be the answer to part A. The highest point that the bomb reached was 200.09 feet. So it didn't go didn't go up much further, but it did. And then it started its journey down. Now, the next question was how long until kaboom, right? So that should be a time. And that's going to be our x-intercept, right? This x-intercept, if you look at it, at the x-intercept, what's the height? What's the height at the x-intercept? 0, right? Which means you're on the ground. So what we're looking for here is the x-coordinate of that point. And that, since that's one of our x-intercepts, it's the 3.55, correct? Well, I shouldn't say x. I should say what? T, right? Because it's time. And time is measured in seconds. And that would be your answer to part B. Okay? Any questions on this? Think you could do that on a test? Now, on a test, I'll probably give you a better function. The numbers here were kind of weird. 200.09, it's hard to graph that. I'd make a problem on the test a little different, so that your numbers would work out a little bit better. Okay. I think I'm ready to answer now any questions over homework. The last one. You know what? I don't think I have. Well, no, I do. Never mind. That would have been, what's today? Day 11? Yeah. The last one, the 2x squared minus 5x plus 4. That one? Okay, 2x squared minus 5x plus 4. Was there anything specific about this one you wanted me to go over, or? Okay, so it opens up, right? The vertex H should be negative 5/4, which is negative 1.25. Is it okay if I don't work this? Or do you want this worked? Tell me. I don't. Yeah, okay, thank you. All right. Thank you. Then K would be what? Plugging 1.25 in there? So I'm doing this on my calculator. Uh, 0.875? Okay. 0.875. All right, so third step would be do a quick sketch. I go out 1.25, I go up 0.8, and I got it here, and it opens which way? Opens up? Which means what? No x-intercepts. So I can see why you would have a problem here. Yes? No x-intercepts. But you do have a y-intercept, so I'm going to put here no x-intercepts. So I'm not going to go try and find them, right? If I don't have them, don't waste your time. So on step 4, my y-intercept, I just plug 0 into the function, I get y equals 4. Okay, so now let me go to a graph. Everyone okay with this? Okay, on my graph, here's what I know. I go out, let's see, here's 1, let's say here's 2, let's say this is 1, Oh wait, I have a y-intercept of 4, so I'll count this as 1, 2, 3, 4. Y-intercept was 4. X-intercept was 1.25 and then 0.85, right? Which would vertex. Sorry, thank you. My brain ain't working yet. That should be my vertex. 1.25, 0.875. And then my y-intercept is here, that dot there. And that's all you have, right? That's all you have. So the way you can do this, there's several ways. Most books will tell you to just take any other point and plug it into your function so you can get another point. But the way I do it is I say, well, I know that I've got to go and do this, right? Well, something like this. Yes? And it has to be a mirror image. So what you could do is kind of maybe with a piece of paper, like, fold a piece of paper or your finger, whatever it is, kind of do a rough measurement of how long that little red dotted line is and just mirror it over that yellow. So do the same length on the other side and you should have a point there also. And that's using the symmetry of the parabola to get another point, and that is it. That's all you'd have to do for that. Okay? Any other issues?
Basically, couldn't you just go 1.25 to the right?
Yes. Yes, you could. Yep. But I mean from that same height, 1.25. So it should actually be at like, what, 2.5 or something? All right, well, we are going to now move away from quadratic functions, and we're going to our next type, which is polynomial functions, right? Polynomial functions. So here we go. Now, I do this very different than the book. And I have my own reasons, all right? But so this is kind of I'm blending like 3 sections together here and kind of picking the order. I'm starting like in polynomials, and then I'm going to go back to 3.2, and then so don't worry about where I am in the book, just pay attention to the idea. So polynomial functions, the first thing I'm going to do is define them, all right? And to define them, I'll ask you to remember the 2 types of functions we already know. The first one was linear. Linear functions look like this. F of x equals mx plus b. An example of this would be f of x equals 3x minus 7. That's a linear function, right? How do we graph that? How do we graph a linear function? It is a line, but how would I graph 3x minus 7? Don't remember? If you have y equals mx plus b, how do you graph it? Okay, use the rise over run. But before you can do rise over run, you have to get the y-intercept. So what's the y-intercept of that line? -7. So you go to -7 on the y-axis down, right? And then from there you do rise over run, up 3, right 1. Up 3, right 1. That's how we graph those. Okay, a good weekend, huh? Quadratic functions are what we just studied. And we could have this, ax squared plus bx plus c, or the other form was ax minus h squared plus k, right? Examples of those, I'm just going to give one example, would be x squared minus 4x plus 4. That's an example of a quadratic function, right? How do we graph quadratic functions? Well, you figure out if it's in standard or non-standard form, right? If it opens up or down, vertex, quick sketch, x-intercepts or not, y-intercepts, sketch, right? So we have the steps for that. That should be fresh in our minds. Now we get into the new thing, which are the polynomials. So here's what a polynomial function looks like. And you're not going to like it. And just keep in mind, with linear, what did I have? Go back to linear. I had the highest power of x I had was that x right there, right? I just highlighted. It was x to the first power. That's what made it linear. With quadratics, we always turn out having x and then somewhere in it it's squared, isn't it? Yes? In the linear, the m was just a number and the b was just a number, right? And then in the quadratic, the a, the b, the c were all just numbers. So keep that in mind as I write this. A polynomial function looks like this. F of x equals a, so far that's okay, right? Subscripted with an n, x to the n. So what that is, okay, don't freak out. The x to the n is just a power on x, right? Like for the linear function, we had x to the first power. For quadratic, x squared. For the polynomial, it's x to the n, isn't it? For linear, the m was a number, wasn't it? And for quadratic, the a was a number. Well, guess what a sub n is here? It's just a number, okay? So I have a number in front of x to the nth power. That's polynomial so far. That okay? Plus a sub n minus 1 x to the n minus 1. All right, so before we throw up in our mouths, that's gross. What is x to the n minus 1? It's just x to a power, right? But n minus 1, isn't that 1 less than the power on the previous one? Right? So it's kind of like if you go back up to quadratic, see how we had that x right there with the b in front? Wasn't that x 1 power less than the x squared? That's all this is saying. X to the n minus 1 means 1 power less than the previous one. And what do you think a sub n minus 1 is? It's not that number by 1. It's just another number. I don't know what it is. It's just some other number. It could be a 5. It could be a 3, a negative 2. Doesn't matter. Nope. Hang tight. You'll see. I think the most complicated part of this whole thing is the blue part. The a sub n, the a sub n minus 1. Because you're not used to seeing that notation. Plus a sub n minus 2 x to the n minus 2. So what's happening there? Taking the power on the x down again, right? This time by 2. So if that first one, if the very first one, x to the n, if n was 7, right? That second term would be a 6 on the x, and the next one would be a 5, wouldn't it? Plus, oh, wait, I didn't say. The a sub n minus 2, that's just another number, okay? Plus a sub n minus 3, x to the n minus 3. Which is just the x 1 power down again, isn't it? And then, after that, plus dot, 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 which means, well, not forever, though, because think about n. Isn't n's going to be a power, isn't it? So, like I said, if n was 7, the next one would be a 6, and the next one would be a 5, and then a 4, and then a 3, and then a 2, and then a 1, and then no x's, right? So what you get, the dot, 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 means continue that pattern until you get down to a sub 1 x to the 1 plus a sub 0. So the x to the 1 would be an x to a power, just the power 1, some number in front of it. And then what's the last one over here, a sub 0? There's no x there, right? So it's just a number. Okay? So here's what I have underneath this. A sub 0, A sub 1, A sub 2, A sub 3, all the way out to A sub n are just numbers, right? And those are all my blue highlighted things, right? All my blue highlighted things are just numbers. Agreed? And then I have one condition here on those numbers. A sub n cannot be 0. A sub n, isn't that the one right in the very front over there? That can't be 0. If it's 0, then this is no longer, then that term's not there, right? So we want to make sure that first term is there. So as long as that first number in front of x to the n is there, then we have a polynomial. Now, does it say anything about the other numbers? Like, could a sub 1 be 0? Yes. Could this one, I'm going to run this. Could this one be 0? Yes. Okay. It's just that first one can't be 0. Y'all still there? N is called the degree of the polynomial. And basically, it is the highest power of x. The highest power of x that you see, okay? The biggest power that appears is your degree. We also have some conditions on n. N must be a non-negative integer. And in case you don't know what a non-negative integer is, it's 0, 1, 2, 3, 4, and it can be as big as you want. Okay, so let's just recap what a polynomial is. A polynomial is basically a function that has x's to powers, right? And those powers that you have to be non-negative integers. So you can't have x to the negative 2, or you can't have x to a fraction. It must be a non-negative integer. The biggest integer we would see in the function is called the degree. All right? And the one condition we have is that whatever that highest power is, right, can't have a 0 in front of it. If your polynomial, if it looks like that, it's a polynomial function. Now, I'm gonna address the blue in a second here, but let's do some examples so you see it's not as bad as it looks. All right? Here's an example. F of x is equal to 7x to the 8th minus 14x to the 6th plus x cubed plus 3x squared plus 1. Is that a polynomial function? Yes. Because every power of x is an integer, isn't it? Non-negative integer. All those powers, 8, 6, 3, 2, those are all non-negative integers, so we're good. And what's the highest power? Okay, that's our highest. So what's the degree of this polynomial? The degree is 8. With me? How about this? F of x equals 1 minus x minus 3x to the 4th. That is a polynomial function, right? What's the degree? Fourth degree. So that's a fourth degree polynomial. I'm going to do the next one right. Well, you know, I'll do a different page. Here we go. I'm going to switch to a new page. How about this one? F of x equals 5x squared minus 9. Let me add something to this. Make it 9x plus 2. I mean, if I hadn't added the x plus 2, it would still have been a polynomial. But I want you to look at this. Does this have x's to powers? Are those powers integers? 2 is a non-negative integer, right? And then, of course, that's a 1 right here. So that's a non-negative integer. And the 2 by itself is okay, because in the polynomial, remember we had the a sub 0 was a number by itself? But you might be asking yourself, well, wait a minute, hold on. Because we studied this already, didn't we? This is a quadratic function, isn't it? Well, it turns out that every quadratic function is also a polynomial function. So, well, just wait. What about this one? F of x equals 4x plus 7. Yes. What's the power on that x? 1. 1 is a non-negative integer. That is a polynomial function. This means that every line is also a polynomial and every quadratic function is also a polynomial. What are the degrees of these? This one was 2 and this one was 1, wasn't it? So here's a way we can look at this, all right? Just to try and get some idea of what the hell's going on here. We studied lines, right? And we know that the graph of lines are completely different than quadratics, right? Those graphs look different. So if you were to like break them up, like you're splitting up, you know, boys and girls or whatever, you split lines and quadratics. They're distinct, right? But they belong to a bigger group of functions called polynomials. So every line is a polynomial. Every quadratic is a polynomial. But not every polynomial is a line. Not every polynomial is a quadratic. So the lines are when your n is 1, and your quadratics are when n is 2. Everything outside of that is just a polynomial. So you could say that a quadratic function is a second degree polynomial, that a line is a first degree polynomial. But a third degree polynomial is not a line or a quadratic. Okay? That's where we are. That makes sense? Now let me get back to why mathematicians would use such an ugly notation for a polynomial function, right? I mean, like the x to the n, that makes sense. X to the n, and then the next one, n minus 1 for, you know, x to the n minus 1, x to the n minus 2. Like the yellow highlighted there, does that make sense? Each power comes down by 1. Okay, but why use a sub n minus 1, a sub n minus 2? Why use that? Why not go back to the convention we had up here where it was like m in front of x, right? Or a in front of x squared, then b in front of x, and then c by itself. Why not use those letters again? Who wants to get 2-point bonus on the next test? It's not about confusion.
Because if you have higher integers, you have to go down, and you have it's the same thing for the numbers.
Like, why not use a, like in this formula right here with the blue and the yellow, polynomial functions. Why not use f of x equals ax to the n plus bx to the n minus 1 plus cx to the n minus 2? Why not do that? No, it's something more subtle. Well, okay, then let me use, why don't I use some other letters instead of a, b, c? How about use dx to the n, ex to the n minus 1, fx? You know what I'm saying? Like, why not use different letters? Why do I use these weird subscripts? It doesn't seem, it seems like math people are just trying to be mean or something. They're just trying to make everything look complicated. But there's a very simple reason why. Not simple, but very necessary reason.
Because A tells you X is going to be your intercept, right?
Well, we'll have to figure out intercepts. It's not quite it. Why can't I use A, then B, then C, then D? A, B, and C are the same. I mean, they are not the same, but that's not the reason why. Let me try and give you a hint. What's the biggest that n could be? N, the degree. It could be as big as you want, right? So it could be, 1,000,000, or it could be 9,000, right? You'll run out of letters. Exactly. You get 2 points there. I can't do this in general because if I say a x to the n, b x to the n minus 1, c x to the n minus 2, 3, right? And keep doing that, then if I have a 30-degree polynomial, you can't use a, then b, then c, then d because you only have 26 letters. And you're already using x and you're already using f. So now you have 24 letters. You see what I'm saying? So as mathematicians, we know that the n can be any number bigger than 26 if we want. Hey, just leave, please. Thank you. N can be bigger than 26, right? So we run out of letters. What do? So we can't give you a general formula like we did A, B, and C. Can't do that. Right? A, B, and C we could do for sure. Why? Because quadratics stop at 2 for highest power. So we'll always have something in front of x squared, something in front of x, something by itself. So we can use A, B, C. But as soon as we let n get big or arbitrary, then we run out of letters. Okay, so that's the reason why. So if I had n is 30, then my a sub n would be a sub 30, right? Then a sub 29, then a sub 28, a sub 27. And see, if we do it that way, you'll never exhaust. Does that kind of make sense? Okay. That's why it looks so bad. All we have to be concerned about in this class is looking at it and identifying the degree. Okay? All right, next thing. We need to talk about what's called the leading coefficient. Before I do leading coefficient, I asked a question, and I heard different answers about what's the biggest n could be. And I heard infinity and whatever. So this is a question that I've asked a few people. What's the biggest number? What is the biggest number out there? Have y'all seen that commercial where the insurance salesman's sitting there with the little kids at the table? My daughter loves that commercial. I don't know why. She loves it when he goes. The one where he goes like. So the kid says like, the answer was infinity, and then the girl says something like infinity plus infinity, and then it's like, what's infinity times infinity? And then, okay. Anyways, what's that? Well, what is the biggest number? I mean, that's a good question, right? Well, it's not a good question. I mean, it's a good math question. It's not a good question. Just any number, what's the biggest? The answer is there is no biggest number, okay? Infinity is an idea, okay? Infinity is the idea of going forever, all right? But you can't say that infinity is actually a physical number. Like, you can't go find it on the number line, right? Infinity is the idea of going out one way forever. So there is no biggest number, okay? And it turns out that infinity plus infinity is pretty much the same as infinity times infinity. And there's even one that would be better than that. How about infinity raised to the infinity? Because what's infinity times infinity? That's infinity times infinity. What's infinity raised to the infinity? That's infinity times infinity times infinity infinitely many times, right? But all of these are the same. It's all the idea of infinite. Neither one of those three things are numbers. So that's just an FYI. I'm teaching my 4-year-old there is no biggest number. I always ask her, what's the biggest number? There is no biggest number, Daddy. All right. You got that down.
Just wait. Wait till she gets to like second grade. What's the biggest number you know? There's no biggest number, teacher.
Keep counting. I'll come back. Okay, leading coefficient. So let's get back to this. F of x equals a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, plus dot, dot, dot. I'm just going to write that. That's a polynomial function, right? That ugly thing. I want to define for you quickly what the leading coefficient is. The leading coefficient is the number in front of your highest power of x. Okay, the leading coefficient is the number in front of the highest power of x. And we will abbreviate it from here on out, LC. Leading coefficient. That all right? So would you agree with me that the degree is pretty easy to find? And wouldn't you agree that the number sitting in front of that should be pretty easy to find? So there are two things that I can ask you for right now. Degree and leading coefficient, that should be pretty easy for you to determine. And we'll go back and look at those two right there. What is for the first one, the 7x to the 8th minus 14x to the 6th, what's the leading coefficient of that one? 7. Okay? How about on this next one down here? -3. -3. Okay? So I put the one on the bottom I put in a weird order to try and trick you. So you might pull the 1 because you think it's the first number I see. It's not the first number you see. It's the number in front of the highest power of x, including its sign. Okay? Okay, so that bottom one, degree is 4, -3 is the LC. The top one there, degree is 8, LC is 7, right? I'll put LC here. LC is 7, and over here, LC was -3. And degree was 4 here. Okay, now what is our ultimate goal with polynomial functions? I mean, what was our ultimate goal with quadratics? To graph them, right? Our ultimate goal here is going to be to graph these, right? So right now, we actually have a lot of what we need to graph. Just the degree and the leading coefficient is a lot for us to be able to determine what it looks like. So I'd like to, before I get into where it's going to get real tough, go back and show you this thing that I'd kind of gotten into a while back. Where is it? Polynomials. Remember this? Okay. I said we're going to do this later and all that. Well, later is today. So I want you to notice something about this picture I have here. Okay? This graph, if you read it like from left to right, it's like a roller coaster. You go down, then you go back up, then you go back down, then you go back up, right? This left side where you go up and this right side where you go up, it actually goes up in both sides forever. So what I'm going to do right now is I'm going to zoom out a little bit. Look at how high this is. 5,000, 10,000. Look what's happening out the right side. It just keeps going up and the left side keeps going up, doesn't it? And if I keep going further and further, well, that's as far as my thing goes. It still goes up to the right and up to the left, doesn't it? Okay, I'm going to go back to where it looks a little better like this. Let me just change the polynomial to a different one. Okay. Look at this one. What does this one appear it's doing on the left and on the right? It's going down forever on the left, and over here, going up forever. And if I zoom this one out, well, that doesn't really do. That kind of misleads you a little bit, but it's still going down on the left, right, and up on the right. Okay. Let me change one thing here. Okay, look at this one now. What's that one doing? On the left, up, and on the right, down, right? And I can sit here all day long, and I can mess with all these little toys I've got in here. And basically, no matter what, you're going to have one of four possibilities. You're going to have either both sides go up, right? See that? Left side and right side both go up forever, don't they? Or you're going to have both sides go down forever. Left and right sides go down. Or you're going to have the left side go up forever, right side go down. Or the opposite of that. Left side go down, right side go up. All polynomials have to have one of those four things happen. Okay? One of those four. That'll be the easy part for us, to determine what's happening on the left and right. The hard part will be determining all this wiggling stuff going on in the middle. Okay? So we can actually do that with what we know right now. And it's called the leading coefficient test. The leading coefficient test. And I will abbreviate this LCT. It's the leading coefficient test. And here's the way that I will present this test to you. I'm going to draw it in the form of a table. And you're allowed to have a cheat sheet on the test, so I would recommend that you put this table on your cheat sheet. Just copy this down. Degree even, degree odd. What's the degree again? What's the degree of a polynomial function? It's the highest power of x, right? But it has to be like 0, 1, 2, 3, 4, 5, 6, 7, 8, right? Positive integer. So if I give you a positive integer, say 7, it's odd, right? But if I give you 8, it's even. So no matter what, if you're looking at a polynomial and you look at the degree, it's either odd or even, right? Okay, so this table is going to have those two cases to look at, even and odd. And then on the left side of this table, the LC being a positive or the LC being a negative. What's the LC again? The leading coefficient? It's the number in front, right? The number in front is just some number, isn't it? It could be 55. It could be -2, -3, right? Can it be 0, though? No, because remember we said the number in front of the highest power can't be 0. So no matter what, the number in front is either going to be positive or negative, isn't it? It's either a positive number or a negative number. So what we've done is we've broken down a table like this, and look at, there's 4 squares left. And those 4 squares represent the 4 possibilities. So the first top left square is this. Up and up, with the question mark in the middle. And then below that, down and down with a question mark in the middle. And then the top right is down, then up, question mark in the middle. Bottom left, up, then down, question mark in the middle. And in the bottom corners of each of those boxes, I'm going to give you an example. X squared. This one, negative x squared. This one's like x cubed. And this one's like negative x cubed. Now I'm going to put this mic down and get up here and show you what I'm talking about here. Look at x squared has a degree of what? Degree. The degree is 2, so it's even, isn't it? And what's the leading coefficient of x squared? 1, which is positive. And we should all know what x squared looks like, right? Up, up. Now, we actually know what the middle of x squared looks like. It's parabola. But that can help you remember even positive looks like parabola, except the middle we may not know. And then if you put a negative in front, what does a negative in front of a function do? Flips it over the x-axis. So now it's down, down. Then x cubed was one of our toolbox functions. And if you remember what it looks like that, right? So down then up. And if I put a negative, it flips everything over. So instead of down, up, it's up. That's it. Okay? You get that? Mr. Roboto. All right, so although this gives us a lot of information, right, about the left and right sides of our graph, there's still a whole lot we still have to determine, which is that inside question mark, right? Now, this right here, this whole thing, everything in here, is referring to what's called the left and right hand behavior. So when we're talking about polynomial functions and we start asking, hey, what's the left and right hand behavior? I'm saying, which of these cases is it? Does the left side go up or down? Does the right side go up or down? That's left hand and right hand behavior. Got it? So let's take some examples. Example. Let's say I wanted you to sketch this polynomial function. X cubed minus 5x squared plus 3. Well, you know what? Let's make it minus 4x plus 20. Let's say I wanted you to sketch that, okay? I'm not giving you the steps for sketching yet, okay? I'm just getting you to think about this. What can you tell me so far about this? Okay, degree is 3. The LC is 1. And according to our table, what would the left right hand behavior be? It would be left side down, right side up, and in the middle, I don't know. Right? That's now, if you draw a graph, and I'm just going to draw a real quick one under here. Here's what I can tell you about this graph. Eventually, this left side goes down. Eventually, that right side goes up, right? I don't know what's happening in the middle, but that's the general picture. What are some possibilities here? We could have that this graph does something like this, comes up, and maybe it comes back down, does that, right? That seems like reasonable. It could do that. Or it could go way up, or it could do, maybe it could do this. Instead of going up and crossing there, it could have come back down right? Then it could have come like this. That's reasonable, right? I mean, maybe it did something crazy like this. Maybe it went up and then back down and then back up and then back down and then back up. I mean, there's a lot of different things it could have done. Do you see why the question mark is still there? We don't know what happens. But would you agree that in all of those pictures, I'm crossing the x-axis somewhere? And if we had x-intercepts, it would really aid us, help us in getting a better picture. So x-intercepts are going to be the main part of the question mark. To determine the question mark, really we're just going to find the x-intercepts. So how would you find the x-intercepts? I'm going to put a question mark here. X-intercepts, where are they? Do I have them? How do you find the x-intercepts for a quadratic? Set the function to 0, right? So let me do the same thing. For x-intercepts, let me set my function equal to 0. And my function was up there, it was x cubed minus 5x squared minus 4x plus 20. I need to set that to 0. Yes, because there's 3 terms, right? 4 terms, sorry. 4 terms. So let's try grouping and see what happens. So if I group, I'm basically taking right after the second term, I'm trying to factor something out of x cubed minus 5x squared. What factors out of the first 2 terms? X squared, what are you left with? X minus 5. Okay, now what factors out of the second 2 terms? Negative 4, and you're left with x minus 5. So I pulled an x squared out of the first 2. I pulled a negative 4 out of the second 2. Do you all agree with that? And now that these 2 things match, my next line is x minus 5, then the x squared minus 4 in parentheses, right? And then the x squared minus 4 is a difference of squares. So factoring has peeked its ugly head out again at S. And now you set each factor to 0, right? So I set x minus 5 to 0. I set x plus 2 to 0. I set x minus 2 equal to 0. So what are your 3 x-intercepts? 5, negative 2, and 2. 5, negative 2, and 2. No, this is pretty much it. Okay? This is pretty much it. So watch what we're going to do now. Okay? We're going to take this information and we're going to just draw a quick graph again. Trust me, we're going to have time. We're going to have a formal set of steps and everything, but right now I'm just trying to, again, get you to think about what we can do. Right now I have x-intercepts where? 5, 1, 2, 3, 4. Here's 5. 2 and negative 2. That all right? I'll put those in blue. I have that so far. I also know that on the left side, left-hand behavior, it must go down and the right side must go up. So from that left x-intercept, I know I go down. And from the right x-intercept, I know I go up. Now it may go up really steep or it may be a little flatter. This class is not about finding this thing exactly. It's getting a rough sketch of what's going on. All right? That's what we're trying to do. Now we run into a bit of a problem because it could do several things right now. It could do this, couldn't it? Don't write this, okay? But it could do this, and this seems like the most reasonable, doesn't it? It could do that. It might be that easy. But it might also do something like this. It may come up on the bottom here on that negative 2, It may come up and it actually may just touch it and bounce off. Remember how our parabola, sometimes you could get the vertex to just touch the x-axis? It could just bounce off there, and then maybe it'll come up and cross through here, and then maybe it goes and it bounces off there again. It could do that. And there's several other variations that it could do, right? So one thing we still need to resolve is whether or not at each x-intercept, do I cross through or do I bounce off it? Like in my picture here, in the green one, what happened at -2? Did I cross through or did I bounce? With the green one, I crossed through. And then at +2 on the green one, did I cross through or did I bounce? I crossed. And then at 5, did I cross or bounce? I crossed. Do y'all see that for the green one? Okay, how about for the black one? At -2, what happened? Bounced, and then at 2, crossed, and at 5, I bounced. Okay, so all we're going to have to do now is determine if we cross or bounce. And there's a way to determine that. And it's pretty easy. You ready to see it? Okay. I'm going to go back to this right here. I'm going to come back to when we factored it. Okay, take a look at those factors right there. Those factors are what helped us get our x-intercepts, right? The x minus 5, we set it to 0. The x plus 2, we set it to 0. The x minus 2, we set it to 0. All you have to do to determine if you cross or bounce is look at the power on each factor. So I'm going to highlight these in yellow. What's the power on x minus 5? It's a 1, isn't it? And then what's the power on x plus 2? It's a 1. What's the power on x minus 2? It's a 1. Okay? I'll highlight them. 1, 1, 1. It will turn out, and I'll write this down formally later, it turns out that if those powers are odd numbers, you will cross. If they're even, you will bounce. That's what it'll turn out to be. I'll just state it now, but later on I'll formalize it. Actually, I want an arrow from the power. If it's odd, you cross. If it's even, you bounce. So let me go back to my picture here. I'm going to erase the green and the black here. If you want, you can, you know what, I shouldn't have even done all that. Let me just do this. I'm just starting a new page. I have 2, 3, 4, 5, -2. I'm just doing a real quick new sketch. I know the left side I go down, right? I know the right side I go up. And I know that at each of those I do what? Cross. So when I draw this, I'm going to draw the left side down, right? But I'm going to keep in mind that when I get up there, I'm going to cross. So I don't need to start like curving it to bounce. I just go straight through it. So I cross through, right? And then it doesn't matter how high I go, okay? And it won't matter for you on a test. You just need to come back and cross through it too. Take calculus and you'll figure out how high it goes in there. Okay? And I'm not even going to care about the y-intercept anymore. Because even if you knew the y-intercept, you still don't know a lot about the rest of the graph. So like I go through that 2 and I cross through. That puts me below the x-axis. So now I've got to get back up to that 5, so I need to curve back through. And then I go through like that. That would be what I would expect on the test, right there. Okay? I know. I'm not sad like everyone else. Like there are a lot of people who are like all upset. Oh, you haven't? Okay. Okay. Yeah. I thought it was good. All right. You ready? That okay? I want to show you with my program. This was my program I made, right? That I told you about. I think you might understand how this program works now. The first thing you do is you put in the degree. What was the degree of the problem we just did? 3. So I put in 3. What were the roots? Those are the x-intercepts. What were our x-intercepts? -2, +2, and then my third root was 5, wasn't it? There's the picture. Okay? Now I can zoom this. I don't want to zoom too much. Look at that. That's if it was drawn to scale. Like, you know how I said I don't know how high it goes? Like, if you count, 1, 2, 3, 4, 5, ticks this way, and the same 1, 2, 3, 4, 5 that way, the highest point is way the hell out there. So we can't get that precision. If I change scale, look, you would have to go all the way up to 200, near 200 to get to that maximum point. You don't need to worry about that. Questions? When you take calculus, you find the maximums. These points are called local maximums and minimums, and you find those. All right. Yes? Yeah, no, not yet. I want to do one more, and then I'll give you homework. I want to slightly adapt that same problem. This is kind of fun, isn't it? It hasn't gotten bad yet. It's going to get real ugly next time. But it's okay. We're going to be fine. All right, next example. Let's try and do a quick sketch of x cubed minus 2x squared minus 4x plus 8. Now that looks very familiar, or very similar to the problem we just did, doesn't it? I mean, it's cubed, so it's third degree. Leading coefficient's 1 again, isn't it? So this has the same exact left and right hand behavior. I'll write that down. Degree is 3. Leading coefficient is 1, which means my left side goes down, my right side goes up, in the middle I don't know. Now, we said that the other thing we would need are x-intercepts, right? So let's find x-intercepts. So I set the function to 0. And since there are 4 terms, I will do grouping again. I'll factor out an x squared out of the first one, and I'll factor a -4 out of the second one. I mean, this is almost identical to the other one, isn't it? Almost. So you pull the x minus 2 out, then you're left with the x squared minus 4. But the x squared minus 4 turns into what? X plus 2, x minus 2? And now you may be tempted to say, okay, just set those equal to 0, right? However, 2 of them are the same, aren't they? So can't I write this x minus 2 squared times x plus 2? You must do that step. You must recognize common factors and put them together to create your squared. Because that's what's going to allow you to know if you bounce or cross. See it? Now set them equal to 0. X minus 2 equals 0. Oh my gosh, come on. X plus 2 equals 0. So you get 2 and -2. And tell me what's going to happen at each one as far as bouncing and crossing is concerned. At 2, I will bounce. And why am I bouncing? Because that power up here on that factor was even. The other one I'm going to cross because the power on this one was a 1, which is odd. I forgot to put even on the other one. One of the mistakes I see people make is that when they're trying to determine the bouncing and the crossing, they look at the number itself. They're like, oh, 2 is even, so I bounce. It has nothing to do with the number itself. It has to do with the power on the factor. And in next class, we'll call that the multiplicity of the root. We just have some technical name for it. Any questions? We're ready to graph. My x-intercepts were what? 2 and -2, and that was it, right? So let me draw some dots here. My left side should go down, my right side should go up. What's happening at -2? Am I bouncing or crossing? At -2, I'm crossing. So I must go down on the left. I must go through -2 and cross, which means I'm going to go to the other side of the x-axis. But then I have to get back to that +2, don't I? And when I get to it, I have to bounce off of it. And that would make sense because if I go up here and bounce off it like this, my right side is then going up, isn't it? And that's what I need it to do. So I've crossed through at -2 and I've bounced off 2. This isn't so bad, or? The problem for us is going to be that the factoring. Because right now I've stuck to things you can factor. Like with this, what if we go x to the 4th? Then we're going to run into some issues. A quick check of this. It's still 3rd degree. I had -2. I had 2, and wasn't 2 a double root? It was x minus 2 and x minus 2 twice. So for my program, I just have to put +2 in twice. There it is. And, oh, this is scaled all wrong. I was wondering why that looked weird. Easy, easy. Okay, there's our graph. There, right there. Okay? That just verifies what we got. I'll save for class next time some more interesting problems. What I'd like to do is send you home with a couple of problems. I'm limiting a lot of this section with polynomials. You'll have very minimal homework out of the book because, like I said, I'm skipping around and stuff. And what I'd like for you to do for homework is sketch the following. Just do what I just did on that last problem for these, okay? I'm going to make these up. F of x equals x cubed minus 6x squared minus 4x plus 24. Number 2, f of x equals, let's see how you handle this. This one won't be so bad, I don't think. X cubed minus 3x squared minus 9x plus 27. Third one. This one you might have some issues with, but we'll see. X to the fourth minus 25x squared. So we haven't done a fourth power, right? We haven't done one. We should still be able to turn left, right-hand behavior. The factoring part of it is pretty straightforward factoring on that. But you'll have to get your multiplicities correct. Make sure those bouncing and crossing. That sound like fair homework? Have it ready to turn in or present to me. Let me do this. I'm going to take a... well, you know, I'll just keep these and I'll give them back to you. The quiz for the graphing. Oh, I didn't collect. Did you turn in the one question? Here, just find yours in here and add it to that.
I have them on the back.